Okay, hello. We are starting a new chapter, new subject, important subject in physics. We had mechanics as the first semester, sort of covering everything that occurred in the 16 and 1700s, and then what we're doing in this course really is electricity and magnetism, everything that occurred basically in the 1800s until about 1900, when basically all of classical physics was understood. So the topics, of course, in this course again are electricity and magnetism, and now we're going to start the magnetism, and we will be doing magnetism for the rest of the semester. So to start with, we should probably talk about what is magnetism. So if somebody asked you what is magnetism, what would you say? Well, perhaps you would say it's the force that exists between magnetic materials. But what is a magnetic material? This is really not an easy question to answer. So we need to start with some observations. And the first question is how do we know that magnetism exists? What is magnetism? That's a little harder to answer, but how do we know magnetism exists? And we should compare and contrast this with electricity and electric charges. So how do we know electricity exists? How do we know electric charges exist? Well, we found that we could statically charge objects, so that when we first started electricity, we took some relatively unsuccessfully, but I was able to show we took some plastic and some silk and some rubber, and we rubbed things together, and we found that we could create what we named electric charges that repelled or attracted each other. In the same way, with magnetism, we observe that there are some materials which will exert attractive or repulsive forces on each other. So the first question you might ask is, well, how do we know those materials are not electrically charged materials? So let me start writing some stuff down. Okay, hold on. Okay, first observation is that we surmise that there's something called magnetic fields that exist because we can observe that there's a force at a distance between two objects. So maybe we pick a stone out of the ground, and we pick another stone out of the ground, and we find that when we bring them near each other, that they repel each other, right? So we can find these materials that just naturally repel or attract each other. And we can further make observations, draw conclusions that this is different than the electric or gravitational forces that we have observed. How do we determine that? Well, first of all, we've determined that gravitational forces between two small stones that we pull out of the ground typically are, we've already determined, Newton determined that the size of those forces, and those forces are extremely small to the point where we would not be able to observe the force between two small stones we pulled out of the ground that we put on a desk, right? But we can observe a magnetic force between two small objects that we can put on a desk. We can observe that it's not an electric force because we've discovered electricity, and we can bring a magnet near an electrically charged insulator, and it will not exert a force on it. So if we bring a magnet, so we know what magnets look like. I mean, typically, your third grade magnet is a bar magnet that has a north pole and a south pole. And if you bring a magnet near a charge, and those two do not exert forces on each other when they're stationary. Try to pull these observations together. So if you have a plus charge and let's just say we have two plus charges, independent of anything else, two plus charges, right? They will exert forces on each other. And let's say you take two materials that we say are magnetic, or where we don't know what it is and we're trying to discover magnetism, whatever, and they will exert forces on each other. So this is my magnet, and this is my magnet or magnetic material, and they exert forces on each other. And then you bring a magnet in the vicinity of a charge, and we find that a stationary magnet does not exert a force on a stationary charge. So a stationary charge exerts a force on a stationary charge. A stationary magnet exerts a force on a stationary magnet, but a stationary magnet does not exert a force on a stationary charge. Magnetism must be somehow different than electricity. Again, we've already argued why it's different than gravitation. So now we have a third force at a distance, right? We had electricity as a force at a distance, electric force as a force at a distance, we had gravitational force as a force at a distance, and now we have magnetism. They're the three forces at a distance that we can measure, that we can deal with in the classroom. The fourth force, remember, is the strong force. I'm sorry, there's a fifth force. There's the strong force and the weak force. The strong force and the weak force are interatomic forces that are difficult to measure in the classroom because they're on the microscopic scale. So there are these five forces at a distance. Now, if you remember when we discussed the fundamental forces, we said there are only four, or maybe even only three fundamental forces. That's because we combine them and we say that really the electric force is like the magnetic force in a lot of ways, and they can be looked at as the same force in some ways. We will see that much later on. For now, the electric force is different than the magnetic force, so electricity is different than magnetism for the arguments that are on this page. Okay, moving on. We have observed that magnetism exists. And we first observed that magnetism exists when people pull these stones out of the ground that repel or attract each other, and they are some kind of magnetized, arbitrarily magnetized. They're called ferromagnets, and there are various things that you can literally find in nature that have that exert magnetic forces on each other. Okay. So, and then of course we have figured out how to make ferromagnets, and the typical kind of ferromagnet that you have played with as a elementary or even as a young child is the typical bar magnet. And with the typical bar magnet, we know that it exerts forces on other things that are other ferromagnetic materials. I'll use the term now. Other things that are magnetic. It exerts forces on them. And what we find is that just like with electricity, there seem to be two, they either attract or they repel. So just like with electricity, where we had some electrical things attract and some electrical things repel, so we gave them the names plus and minus. With magnetism, we gave them the names north and south. It's just the two different things that attract and repel. A north pole repels another north pole, just like a plus charge repels another plus charge. And a north pole attracts a south pole, just like a plus charge attracts a minus charge. So the typical thing is a bar magnet, and ignore the fact that this has yellow and blue. And this is just a piece of metal that's been painted. Did I say yellow? That's red. Kind of other kinds of permanent magnets that you've probably played with before. So the one that you see here is this is probably just a typical iron bar, something that you could pull out of the ground, sort of, something that you can easily make. There are also the neodymium magnets, which is a neodymium magnets, which are the strongest permanent magnets. Oh, I don't think I used the term permanent magnet. Permanent magnet is something that holds its magnetic field, and so therefore is a ferromagnet. A ferromagnetic material is something that holds its magnetic field. Permanent magnets, and they hold their magnetic field. They might get weaker over time, they might not. Neodymiums are the strongest permanent magnets that exist. The ones shown here, I haven't put anything for scale, but these are probably smaller, about as small as a smaller than a dime. So these are small, although the one on the left is thick. But these are extremely strong magnets. Now, the bar magnet, remember, we said it's got two poles. One attracts and one repels another magnet. And the neodymium also has poles, but the neodymiums are a little bit more complicated. We don't need to get into the details, but it might be that we've got a north pole on one side and a south pole on the other side, or it might be that you got a north pole on top and a south pole on the bottom, and those are what are called dipole magnets. So these are dipole magnets. They sort of act like a bar magnet in that they have two poles. It's just like a plus charge and a minus charge. Whoops, that's not a plus and a minus. Charge and a minus charge. If these were charges, that would be a dipole. So your magnets typically come in dipoles, but you can have more than dipoles. You can have what are called quadrupoles. You could have four poles, right? And that would just be like having four charges. and you might have north and south. And you can actually have really complicated where there's a pattern of north and south poles throughout. The neodymium magnets can be, I bring that up only because they can be a little bit more complicated, and sometimes they don't act like a typical north-south dipole. You could also have the horseshoe magnets again, which you might have played with as a kid, and again, it's typically just a dipole magnet that's been bent into a horseshoe shape, north-south, and that is used often to pick up things as a I'm not even sure what I want to say, but it's you know, if you have metal stuff, you often use it to you use the horseshoe magnet, both poles, north and south, to attract things, to pick them up. Okay. Thinking about similarities between magnetism and electricity, if you put other magnetic material or things that react to magnetic materials in the vicinity of a magnet, the other ferromagnets in the vicinity of a magnet, like iron filings, those filings will line up along the field lines of the magnet. And so here I've got a picture of a dipole with iron filings, which sort of show the pattern of field lines. Traced some of those field lines. And look, it looks an awful lot like an electric dipole field. But this is now a magnetic field, which is a different kind of field, creating a different kind of force. We've pretty much talked about the similarities, and seen that electric charges and magnetic charges, right? The electric charge plus minus the magnetic charge, north-south. In magnets, we call those poles rather than charges, but you can call them charges just as well. That electric charges and magnetic poles really are very similar in the way they interact with other charges and other poles. And they're similar in the way that they exert forces at a distance and that they exert forces on each other. So what's the difference between electricity and magnetism? Well, first of all, we showed that magnets don't exert forces on charges and charges don't exert forces on magnets when they're stationary. We're going to talk later about movement. You know that when they move, there's something different going on. But in addition, the other difference, which we'll talk more about later, is that if you cut the dipole half, so you have a north pole on one end and a south pole on the other end, it's actually awfully difficult to separate a north pole from a south pole. And what I mean by that is that a dipole magnet, a north and a south on a bar magnet, like a piece of iron, and I just cut that down the middle. So I'm going to have two pieces. Separate those two pieces. It turns out that what I get is I get a north and a south and a north. So I cut a dipole in two and I just get two dipoles. If I try to do that again, how many times I do that, I simply just get smaller and smaller dipole magnets. And so what this tells us is that it's really difficult to isolate a single magnetic charge or a single magnetic pole. It's difficult to get a monopole. And the reason for that is because of the nature of magnetism. The nature of magnetism being that a dipole magnet is really essentially, typically, not always, but typically created by a single charge moving in a circle, classically, by a single charge moving in a circle. We'll discuss that more later. But if you have a single charge moving in a circle and it creates a dipole magnet, you can't take that and somehow make it into a monopole, a single pole. A monopole is a single pole. So typically magnets come in dipoles. And actually, most of physics acts as if monopoles do not exist, although that's not necessarily true. To summarize, there exist electric charges, pluses and minuses. In the same way, there exists magnetic charges or magnetic poles, norths and souths. Pluses attract minuses, pluses repel pluses, minuses repel minuses. Norths attract souths, norths repel north, south repels south. Since electric charges exert forces at a distance, we talk about the electric field, E, that exists around a charge. Because magnetic charges or magnetic poles exert forces at a distance, we talk about the magnetic field, B, that exists around magnets. Magnets can be found in nature, permanent magnets, and magnets can also be created. We'll talk about that later. And they can be created, both permanent magnets can be created and what are called electromagnets can be created. We'll talk about that later. But you get magnetic fields from both permanent magnets and electromagnets. Just take another moment to discuss that at this point. So again, we observe that magnetic fields exist between two permanent magnets. Another observation is that we observe that a permanent magnet does not exert a force on a stationary charge that's stationary relative to the magnet. Okay, so those two are pretty clear observations. The next observation is a little bit surprising. A permanent magnet does exert a force on a moving charge. So there must be a difference between a stationary charge and a moving charge, right? Now, we got to take observation number one and say that, oh no, observation number one, totally wrong, right? Not electric fields. Oh no. Hopefully you caught that. That is a magnetic field. So now we got to say, okay, observation number one is that magnets exert forces on each other. Observation number two is that magnets don't exert forces on charges. Observation number three is that magnets exert forces on moving charges. So therefore, by observation number one, a moving charge must be a magnet. A moving charge creates a magnetic field. So that is an amazing, sort of cool observation. Moving charges are magnets. Comes back to this concept of the fact that we have permanent magnets and we have electromagnets. An electromagnet is a magnet created by moving charges. And where do we find moving charges? Well, you can find them all over the place, but particularly in wires, right? If we put moving charges, if we put a potential difference across a wire, we move the charges, and so therefore wires that carry currents are magnets. And that is what an electromagnet is. An electromagnet is a current carrying wire. On the same page, we're going to go from here up to here. I'm going to erase that arrow. But wires that carry currents are magnets, and that's what an electromagnet is. So you can create a magnet from current carrying wires. And just is a magnetic field around any circuit. There are magnetic fields in the vicinity of circuits. They aren't necessarily terribly large, especially as you get farther from the wires, because the magnetic field of a wire goes as 1 over r. It falls off as 1 over the distance. But you can indeed, put a lot of current carrying wires near each other and make a much larger magnetic field, and that's typically what we think of as an electromagnet, is when we form a wire to make a large magnetic field. We'll talk about that later. But this is the basics of magnetism. Let me fix this to make that clear, that the magnetic field goes as 1 over the distance from a wire when you're near a current carrying wire. Covers it for the basics of magnetism. We'll get into some more of the details in the next couple classes. Have a great day.